Okay, just have a look at page 1. Okay, have a look at page 1. We'll just start doing the questions one by one. All right. Now you have a team of 9 dogs that can pull a sledge with a combined force of 800 Newton at a speed of 1.5 meter per second for 360 minutes. What's the average work done by each dog during this time? Okay, they want only for one dog, but you have 9 dogs here. All right. So they want the work. What you learned was that power is W over T. Power is also FV. Okay, so right now you actually want work done for one dog. Okay, what you can do is that you can do it both ways. I'll just show you 2 different ways of doing it. Now you have speed and time. All right, they tell you this the speed of 1.5 meter per second for 360 minutes. That means for that entire 360 minutes, the speed is constant. Now, what can I get from these two? The time and the speed. Velocity, sorry, let me use a different color. Velocity is distance divided by time. Or maybe I better just use S now. Okay, S divided by time. Displacement divided by time. S is Vt. You have velocity 1.5. You have time 360 minutes. Change to seconds. That means you need to multiply by 60 seconds. What you're going to get is 1.5 times 360 times 60, giving you 3,240 meter. Wait, am I doing something wrong? S is Vt, S is Vt 1.5 meter per second, 360 minutes. Yeah, you're going to have 3,240 meter. Okay, so if I use power, if I use work equals to force times distance, this one is the force by 9 dogs. Okay, so if I want to find out the work done only for one dog, I will take 800 divided by 9, because this one I only want the force for one dog, then multiply by the distance moved. So this one will be 800 divided by 9 times 32,400. I'm gonna get 2.88 times 10 power 6 joules. Okay, this one is for one dog only. Right? The answer should be C. Now, there's another way in which I can do this. This is another different way in which you can do so. If I say that power is equals to force times velocity, as I mentioned to you, the force is of 800 Newton is for 9 dogs, by 9 dogs. All right, I only want to consider the work done, or yeah, I only want to consider the case for one dog, right? So if I say power equals to FV for one dog, this one will be 800 divided by 9 times 1.5. 800 divided by 9 times 1.5, giving you 133.3 watts. Okay. This is already for one dog. power provided by one dog. So power is work divided by time. You take 133.3 equals to W divided by 360 minutes times 60 to change it to second. Your work should be the same thing. You're going to get 2.88 times 10 power 6 joules. Okay, so you can work it either way. Either you use something like this, or either you use something like this. It will still get you the same answer. All right, so this one answer is C. Okay, now for 17, which statement is correct? A ball lands on the ground and bounces. Kinetic energy changes sign because the ball changes direction. Now, is the first statement even correct in the first place? This first statement is wrong because they say kinetic energy changes sign. Kinetic energy is scalar. There is no direction to energy. Okay, here they're saying that kinetic energy changes sign because the ball changes direction. This is wrong because kinetic energy is scalar. There is no direction. There's no negative KE. All right. Therefore, no sign to consider. Only when you are vectors, then you have positive, negative signs because you need to make sense of the direction. Which one is positive direction? Which sign is negative direction? Okay. Then after that, we go to part B. A car drives up a slope at steady speed. Keyword here is steady speed. Okay. Constant speed. All right. They tell you the power generated by the engine equals the potential energy gain per unit time. Equals to the potential energy gain per unit time. This is actually referring to your GPE. Okay. Now, this statement is also wrong because of some issues here. Let me clear off everything, right? Because it's too messy, right? B is wrong, A is wrong. This one I told you is constant speed. Okay. Now, if you have a car that you drive up a slope, all right. If you have constant speed, this is your force F. Okay, the power generated by the engine must be equal to the potential energy gain per unit time. Now, let's just say that this is the force exerted by the engine. Okay. Now, if the force exerted by the engine, all right, the force exerted by the engine causes your car to move from point A to point B, taking it a distance of S. All right, and then when you move from point A to point B, you have a change in height of H. Okay. The part where you have constant speed already implies that there is friction. Here there is friction. All right, because you see, if this is the force of your car engine, if I say that there's no friction, my car will actually start to accelerate. Okay, my car will accelerate, the speed will not be constant. You see, the question here specifically told you that your car is driving up the slope at steady speed, meaning to say it's constant speed. Okay, if you look at the diagram a little, if this is my car and the engine is exerting a force to push the car outwards, If the force of the engine is the only force present, I have a case where nothing is opposing the force of the car engine. I have a net force. Maybe I use a different color. I have a net force, therefore an acceleration. So speed cannot be constant. But the case is that speed is constant here, right? So the only way that speed can be constant is if there is frictional force. Okay, frictional force opposing your motion. All right. In your case, it will be force of the car engine equals to your frictional force. All right. The part where we have a constant speed going up the slope already implies that we must have friction in the first place. If without friction, we would not be having constant speed. We would be having acceleration because the force from the car engine is the net force, which in turn causes acceleration. Okay, so there is going to be acceleration. If we want to talk about the energy changes that occur, this is where the examples that we went through just now will come into play. The work done by the engine will be equal to the gain in GPE. In general, I can say this: change in KE plus work done against friction. Okay, the work done by the engine could be used to increase the GPE, increase the KE, as well as work done against friction. But because this is steady speed, constant speed, I already know that change in KE is 0. So this one is out. What I actually have is just work done by the engine is increasing the GPE as well as work done against friction. Why is there increase in GPE? Because there is increase in height, therefore GPE increase. Why is there friction? Why is there work done against friction? Because there is friction, therefore work done against friction exists. So I have these two terms. All right. So if this is in terms of energy. If I want to convert it to power, because you notice that the term here is power, right? If I want to convert it to power, what I just need to do is I need to divide the entire equation by T. Because you know that in power is change in energy divided by time only. So you divide the entire equation by time, you're going to get power of the engine is equals to the change in GPE divided by time plus work done against friction divided by time. Okay. So the statement here is that the power generated by the engine is equal to the potential energy gain per unit time. What you see here is that the power generated by the engine is equal to the potential energy gain per unit time plus work done against friction per unit time. The part where we say that potential energy gain per unit time is actually this one. Okay, so this is the potential energy gain per unit time. You can see the power of the engine is not equal to the potential energy gain per unit time only. It's actually equal to the potential energy gain per unit time plus work done against friction per unit time. So that's why answer B is wrong. Okay. Okay, then I move on to the next statement. Answer choice D is definitely wrong. This one has definitely nothing to do with energy at all. Okay. It's impossible for momentum to be conserved in a collision. Okay, so this is a weird one because it's not talking about energy, it's talking about momentum. But even if you consider it as it is, they say momentum is not conserved in a collision. It's impossible. This is wrong. This one can be. This one, what we'll say is that momentum is conserved in a closed system. Okay, in a closed system. We learned that under conservation of momentum, total momentum before and after collision is conserved. That total momentum before and after a collision is always conserved in a closed or isolated system. Okay, it will be conserved in a closed system, but here they say impossible to be conserved. This is definitely wrong. Okay, so your only answer choice is C, right? Okay, now an electric heater can be 100% efficient. This is something that is true. Okay, in general, we tell you that nothing can be 100% efficient, right? Not necessarily the case all the time. Electric heater can be 100% efficient because remember just now I told you that when you have a machine, a portion of your energy input will be converted to useful energy output, but then part of it will be wasted. All right. But I also tell you that when your energy is wasted, usually is in the form of heat, this statement here, right? So if I talk to you about a heater, you have energy input, and then you have useful energy output, and then this one is energy that is wasted. It could be that your electric energy input for your heater is electrical, but what you want as your useful energy output is heat. But then energy wasted is also heat. You see? So you see, because of this, you can actually say that efficiency can be 100%. All right? Because even your wasted heat, so-called wasted energy, is also heat, which is actually something that you want. So it can be 100% efficient. The term is can be 100% efficient. Okay? Right? So this is the also a weird one. Okay, they are trying to play around with your mind. Okay, so electric heater can be 100% efficient because your wasted energy is also heat. You want heat in the first place, but your wasted energy is also heat. Okay, so this is for question 17. Okay, then we look at 18, the next question. All right, now the diagram shows a pump called a hydraulic ram. In one such pump, the long approach pipe contains 500 kg of water. A valve shuts when the speed of the water reaches 2 meters per second, and the kinetic energy of this water is used to lift up a small quantity of water by a height of 15 meters. The efficiency of the pump is 10%. Which mass of water could be lifted by 15 meters? Okay, so your long approach pipe has 500 kg of water. The valve shuts when the speed of the water reaches 2 meters per second. And then the kinetic energy of the water is used to lift out a small quantity of water by a height of 15 meters. Okay. So what's happening here is that basically your water is trying to move this way. Now your pump here has something called a valve. Okay. Now if your valve is open, the water that is flowing will just flow like this and go out. Okay, if your valve is open, the water will just flow like this and then go out. This is if the valve is open inside the pump. But right now, what's happening is that they say that the valve is shut. Okay, the valve inside the pump is shut. All right, so your valve right now is shut. It's closed. All right, maybe I better, rather than writing shut, I better write closed now. Okay, the valve inside your pump is closed. So what will happen is that the water that was flowing from your long approach pipe, because this valve is closed here inside the pump, water cannot flow like this. Instead, it will now flow upwards and then go inside here. Okay, so it will now flow like this. All right. So the thing is that when you are moving from here to here, you had a gain in GPE because height increase, and then also you will have a loss in KE because water slows down. Okay, basically when you move from here all the way to here, you understand that you would have an increase in GPE because you have a high increase, and in return your KE would drop because your water is actually slowing down. Okay, even if you don't understand the part where water is slowing down, you must understand that there must be some form of energy that has dropped. Okay, conservation of energy implies to you that when energy is lost in one form, some other form of energy must be gained. Okay, you cannot have both forms of energy loss or both forms of energy gain. If something is lost, something must be gained. Or if something is gained, something must be lost. Okay, that is always true. So the fact is that you have an increase in height. This one is very clear. All right. The reasonable thing to expect that is lost is actually your KE. Okay. So your change in GPE is actually equals to the loss in KE. This one is your gain in GPE, loss in KE. Don't need to bother so much about friction because there's no mention here, so you assume it's not present. Okay, right. So right now what they're telling you here is that your pump is actually only 10% efficient. This is your pump here. Okay, your pump here is this. It's actually converting your KE to GPE. All right. Actually, this one is actually the proper equation for what you have here. Your gain in GPE is equals to your loss in KE plus losses now, but don't bother about this one first. Let's look at the pump first. When your water goes from here to here, it had KE because the speed of the water is 2.2 meter per second. Right? They told you that when the speed of the water on reaching the valve is 2 meter per second, the valve will shut off. So when the valve shuts off, the water will start to flow upwards. So your water here already has KE. Okay, so bear that in mind. The water here already has a KE. There is a non-zero value. All right, so your pump will convert this KE into GPE, but it won't be 100% conversion. Okay, because the pump is only 10% efficient. Let me just write this out for you. If pump is 100% efficient, that would mean that change in the loss, sorry, the gain in your GPE is equals to your loss in your KE. Okay, this is if the pump is 100% efficient. But if the pump is not 100% efficient, this is what you're supposed to see. Okay, not all your GPE gain, sorry, this is, yeah, not all your KE loss, the KE that you lost, wait, now let me just write this. Your GPE gain, oh, sorry. There's a mistake here. This one would be losses or change in KE. Okay. Yeah, this is the correct one. My mistake. All right. If your pump is not 100% efficient, whatever KE that you lost, part of it will be converted to GPE. This one is some other energy losses. All right. This is another different form of energy loss. Okay, so not all your KE will go into GPE because some portion of your KE loss has gone into some sort of other energy loss. All right. So you won't really be using this equation to solve this question. You won't really be using this equation to solve this. Instead, you use a different one. Okay, you will make use of the concept of efficiency, right? So what you see here is that the efficiency is 10%, right? Recall the efficiency is P out over P in times 100%. Okay, your P in is actually your, oh sorry, rather than writing P out, I think I should write it as E out, E in. Sorry, I always get this mistake. Energy out over energy in. Your energy out is your change in GPE. Your energy in is your change in KE. Okay, times 100%. So your efficiency is 10%. The change in GP is mg delta H. Your KE is just half mv squared. Then times 100%. So you submit your values. 10 equals to 500 times 9.81 times your height of 15 meter. Sorry, no, sorry, my mistake. The mass here is different. This is your mass that you want to find. And this is 9.81, 15 meter, half 500 times 2 square times 100. So you solve this, you will get this. 0.5 times 500 times 4. Okay, 10 times this answer divided by 9.81 divided by 100. You're going to get the answer as m equals to 0.68 kg. Okay, this is the answer. Okay, now this one is where you need to be careful a bit, right? This mass and this mass is different. Okay, you may be wondering why is it that the masses are different? Shouldn't this cancel off? Why is it that I leave this m here and then I put this m500? There are actually two different things. Okay, maybe I should not have used this. Okay, this one I use a different symbol for you. This one is the mass of water in the pipe. Okay, times v squared. All right. This m is the mass of water in the mass of water lifted. Okay, this m is the mass of water in the approach pipe. This is the approach pipe. You have a mass of 500 kg here. Okay, when your water of 500 kg reaches a speed of 2 meters per second, your valve will close. So the water suddenly stops flowing. From 2 meters per second, you go to 0 meters per second. Okay, so the mass of water that stopped is 500 kg, but the 500 kg of water, not all of it will go up through this pipe here. Only a portion of it will go up. That's what you want to find out actually. So let me highlight some of the stuff again. The 500 kg is here. Okay, your 500 kg is here inside your approach pipe. The mass of water that is lifted up is here. This is your m that you want to find. Okay, that's why here I give you two different things. Your mass is not the same. Your masses will not cancel because you're talking about two different things. All right. From here to here, you had the change in KE. From here to here, you had the change in GPE. All right. a portion of your KE was converted into GPE according to this efficiency. All right. So far, so good. Okay, so the answer is B. All right, 0.68 kg. Okay, right. We continue on to the next question. This is question 19 on the same page. All right. Now you have a conveyor belt that is driven at velocity V by a motor. Sand drops vertically on the belt at the rate of m kg per second. What is the additional power needed to keep the conveyor belt moving at a steady speed when sand starts to fall on it? So we try to visualize a bit on what's happening. This is your conveyor belt, for example. Okay, yeah, this is a very poorly drawn version of it, but you get the idea. Okay, so something is dropping sand onto your conveyor belt. Okay, and then the sand that's being dropped will now start to move along with your conveyor belt. Your conveyor belt is conveyor belt is something like the moving belt that you see in Sushi King. I mean, when you go and eat at those sushi restaurants, you see the moving conveyor belt that brings the sushi around to the different tables. Yeah, something like that. There's a moving belt. Okay, so sand is being dropped onto the conveyor belt. Okay, this is your conveyor belt. Okay, let me write properly. This is the conveyor belt. Okay, the conveyor belt is twisting, so the conveyor belt is turning, so it's transporting sand from one end to another end. Okay, so this part here is your sand. Okay, this is your falling sand. This is your sand being moved. Okay, so the sand is being moved with a velocity of v. All right, to move this sand with a certain mass at a certain velocity v, you need power. Okay, the question is asking you what is the additional power needed to keep the conveyor belt moving at steady speed when sand starts to fall on it. All right, sand is dropping vertically onto the belt at the rate of m kg per second. So this amount of sand that you have here, what's the power, additional power that you need in order to move it at a steady speed of v? Okay, yeah, so the steady speed is v because the question already told you here. The conveyor belt is being driven at the velocity of v by a motor. It could be that this is your motor. So the motor turns, it causes the belt to move. All right. So what's the additional power that you need to keep the belt moving at a steady speed of v once you have sand falling and you move the sand along? All right. So the thing here is that if without the sand, this is without the sand, the motor is already turning and is causing your belt to move with v. But when you have sand, you are adding weight onto the belt. Okay, so if you don't do anything, your speed is going to drop. All right, if let's just say your motor, when you go from here to here, you don't do anything, sand drops on your conveyor belt, your sand has weight, is pushing down onto, is weighing down onto this conveyor belt. If you're still using the same power of your motor, your speed will not be v, your speed will be lesser because you're moving something heavier. Something heavy is on your belt, so you cannot move it as fast. If you want to move it as fast as before, you need to have additional power. That's why the question here says, what is the additional power to keep the belt moving at steady speed when sand starts to fall on it? Okay, what is the additional power that you need? Okay, so that's the story here. Now the power, again, you can make use of a few things. Power, you know, is change in energy divided by time. Power is also work done divided by time. So which one do you want to use? Now you might have considered the fact that if the conveyor belt was moving at speed v, the sand will also be moving with speed v, right? So you may have tried to use this equation instead, where you say the power is change in energy over time, which is in turn the change in kinetic energy divided by time, in which you say it is half mv squared minus 0 divided by t. So therefore giving you half m over t v squared, right? So after that, there's another little annoying thing about your current question. The m here that you see is already mass per unit time. Strictly speaking, in other questions, when you see m, you would have related to mass only. But your question here is trying to make your life a lot harder by saying that m is not mass only, it's mass per unit time. Okay, so let's just say that this one I rewrite it as big M, okay, to avoid any confusion. So this one, power is half m divided by tv squared is going to be this. If you had done this method, giving you this answer, this is actually wrong. Okay, although it seems sensible right now when you say that power is change in energy divided by time, you may have said that, oh, the sand here is moving with speed v. So if I know the change in kinetic energy of the sand as it moves divided by the time, I can get the power. But there's one thing wrong with your assumption now here. Your KE here is not 0. You notice that change in KE must always be the difference in energy between 2 points. So it could be that here your KE is half mv squared. That is correct. But here, we're going to use a different color to highlight it. Your KE here is not 0. Okay, KE is not 0. Okay, because you see this method here depends on you saying that the initial KE is 0. But the fact is that the KE here is not 0 because you see when you try to drop the sand, yeah, you could say here is 0 meter per second, and then here is the belt lah. All right, say here is the belt. When your sand starts to drop and reaches the belt, it already has a certain speed. Maybe this one is 5 meter per second. Here already has KE when it starts to drop on the sand. Okay, maybe I draw it nicer for you. Okay, you know, this is your conveyor belt. Okay, this is your belt. So when your sand is falling, yeah, it falls from whatever is falling from, maybe from rest. Okay, that one will be correct to say is 0 meter per second. But when it falls and reaches your belt, it won't be 0 meter per second, it will be at some speed. Okay, there'll be some speed here. All right, maybe for example, it's at 5 meter per second. So I can say here that green color, maybe I use green color. I would say that this point here, when sand falls, when sand makes contact with the belt, it already has KE. Okay, and sand makes contact with belt, it already has KE. Therefore, KE is not 0, which is the point that I'm trying to emphasize here. Okay, when your sense falls and moves, yeah, no doubt you can say that this part here has KE half mv squared. But this part here, you cannot say that KE is 0 because the KE is not 0 in the first place. When it falls onto the belt, it already has a speed. Okay, so it has a speed already. Its KE is not 0. Okay, so when you say power is change in energy divided by time, change in KE divided by time, so it's half mv squared minus 0 divided by t. This assumption that you have here was wrong in the first place. That's why this answer cannot be correct. Okay, it seems sensible, but it's not correct because the initial K is not 0. So you cannot use P equals to change in E divided by T because you don't even know what is the initial KE here. This is the big question mark here. Okay, so you don't know what is this one here. So instead, you need to rely on this. Okay, so if I rely on this one, P equals to W over T, what is it going to be? Let me just write it out. I'll just use green color. Now P is W over T is equals to Fs divided by T. F is S divided by T. And then after that, you also have, oh, sorry. The P equals to W over T. I want to use this actually. Okay, sorry. Just now I was writing, I'm actually trying to derive back to P equals to Fv. I'm going to use this instead. P is equals to Fv. Now, F you remember as this, right? In the last few chapters, force is rate of change of momentum. Okay. So right now, what you can do is that you base your answer, you change your force into rate of change of momentum. So force is rate of change of momentum, mv. Momentum is mv minus change in mass times with v divided by t given v. So this one is change in mass divided by t equals to v squared. Then this one is equals to mv squared. Your correct answer is this. Okay, let me go to this one. Okay, right. So this is actually the correct method. You see, it relates to what I talked to you about when I was describing force, right? Now, force is rate of change of momentum. Okay, rate of change of momentum. All right. Now, momentum changes when v changes or m changes, right? Strictly speaking, I could say something like this now. Change in momentum is equals to the change in mass times v, or mass times change in velocity. This one is change in mass. This one is change in velocity, right? So right now, what I'm doing here is that power is force times velocity. Force is rate of change of momentum times v. So the rate of change of momentum here is that I'm saying that the mass change multiplied with velocity divided by time gives me force times v again. Now the mass change here is actually just going to be this one Okay, sorry. The mass change here is just going to be the mass that fell onto the conveyor belt. Okay, yeah, maybe I revert what I just said. This is the mass change multiplied with your velocity v. Okay, so I group it again. The mass change divided by the time is actually this one. Because what I know is that this is the amount of mass of sand per second that has dropped onto my conveyor belt. This is my delta M delta T. Okay, the V that I have here is the same V as here. So I can just multiply them together, giving me V squared. All right, so to highlight a bit what I just mentioned, this delta M is actually the mass change per second, which is basically this mass change or mass drop. Okay, mass change or mass drop per second. Okay, which is this one. Okay, so eventually I get that this, which will give me this answer. All right, so this one here is the correct answer. Okay, right, that's the understanding here. Yeah, this is actually one of the harder questions, so don't worry if you feel that it feels very complicated. It is not a standard question that you tend to see. Actually, this first page of the questions that you see nowadays here, the first page of the questions that you're seeing on the first page here, all of them are actually harder than usual. Okay, this is not the standard questions that you will see, don't worry. Right, so the answer for this is D. The working is what I just showed you here, although it looks a bit messy. All right. Okay, so no issues. Then I move on to the next question. All right. Right, so I move on to the next question. So I clear this one off. All right, now June 15 P12, you have a uniform solid block of weight 500 Newton, weight is 0.4 meter, and a height of 0.6 meter. The block rests on the edge of a step of depth 0.8 meter. The block is not over the edge of the step and rotates 90 degrees before coming to rest on a 0.6 meter edge horizontal. What's the change in GPE of the block? Okay, now this is more straightforward. So basically you have a block like this, and then they topple it over to the ground like this, from here to here. What they want is the change in gravitational potential energy of the block. So this one is quite straightforward. Change in GPE is mg delta h. But remember last week what I mentioned was that this is the change in height of center of gravity. Okay, because I made an illustration saying that if you measure the bottom distance or you measure the top distance, that is not necessarily going to be correct. Instead, you have to measure the center of gravity to center of gravity distance for your changes in height. So right now, what I can say is that because this is a uniform block, okay, keyword here is uniform. So COG is at center, going at the center of whatever you are seeing. So my COG will be here. Okay. Half of 0.6 would be 0.3 meter. And then this one here, my COG would be somewhere around here. Okay. My center of gravity will be somewhere around here. Let me just draw this. My COG would be here. This one, half of 0.4 would be 0.2 meter. Okay, note that I can actually just also do this, but this one is a bit unnecessary. Okay, this one I know is going to be 0.3 meter. Okay, what I want as my change in height is this one. Let me use a proper color for you. No color that I can just this one. This is my change in height. Okay, from here to here, I want this one. So what is my distance? Now you see that if I want this height, it's actually going to be 0.8 minus 0.2 plus 0.3. Now this portion here, 0.8 minus 0.2 is this one minus this one. I'm gonna get this one here. Okay, maybe it's better if I just draw it out for you. This is 0.8 minus 0.2. Okay. Now 0.8 minus 0.2 plus 0.3 will give me this entire height. Okay. So mg delta h would just be this one. Mg is weight already. And this is already weight. It's just going to be 500 times with 0.8 minus 0.2 plus 0.3 giving you 0.9. And this is 0.9. Right? 500 times 0.9, you're going to get 450 joules. So answer is C. Okay, so be careful about the changes in height. Use the proper one. And I just highlight it for you. I want this plus with this, which will give me this. Okay, 0.8 minus 0.2 plus 0.3, 0.9 times 500. You're gonna get 450 joules. All right, so this is for this question. So far so good. So this one is okay. Then we go to question 16. Okay, question 16 is something else on energy conversion again. Okay, the diagram shows a hydroelectric power station. The reservoir is linked to turbines by a pipe of uniform cross-sectional area. Water flows from X to Y at constant speed. Which statement about the change in energy of the water as it moves from X to Y is correct? Water is moving, sorry, let me just show you the whole thing. Water is moving from X to Y, okay? Now there's a key term here that you should see. Water is flowing from X to Y. Constant speed means no change in speed, right? When you have no change in speed, no KE change. KE change is 0. Okay. So this one, just see this one first. Okay. So the water flows from X to Y at constant speed. There's no change in speed. The change in K is 0. Which statement about the changes in energy of the water as it moves from X to Y is correct? Now we look at the statements one by one. It gains gravitational potential energy and kinetic energy. This is wrong because I already mentioned to you there's no change in speed from X to Y, so no change in KE. Gain in GP, this is also wrong, isn't it? Because it's saying from here to here, there is decrease in height. Therefore, GPE is dropping. So it is wrong. Now it loses both elastic potential energy and kinetic energy. Don't bother about the elastic potential energy first. The kinetic energy one I know definitely is wrong. So this one is out. Let's go to C. It loses both elastic potential energy and gravitational potential energy. Okay, this one you can say is correct. All right, but what about this? And what about this? All right. Let's talk about the elastic potential energy part now. Is it correct to say that it loses elastic potential energy? Now, the elastic potential energy that they're talking about here, the elastic potential energy that they're talking about here is energy in the form of pressure. In the form of pressure. Okay. To illustrate to you what I mean by that, if I give you a tube, this is just an example. What do I mean by energy contained by pressure? If I give you a very long tube like this, and I tell you that the tube contains water, I make 3 holes on the tube. One here, let's call this A. One here, let's call this B. And then another one here, let's call this C. Now, when I make a hole on the tube, I would say that water will start to shoot out from the holes that I made. Okay, but when you compare the water that shoots out from the 3 different holes, they won't be shooting in the same manner. See, the hole from A would have water shooting out like this. The water from B would be shooting out like this. And then the water from C will be shooting out like this. Okay, notice that for this part here, the water shoots out further. Okay, the water shoots out further. But why is it so? It's because you see pressure is because of the pressure of the water. You learned before this pressure is H rho G. Pressure is actually directly proportional to H. When H increase, pressure increase. So when you compare the heights of HC, HB, and then HC, HC is definitely larger than all the other two. So pressure is definitely higher here. The higher your pressure, the further your water will shoot out. So water shoots out further because it is at larger depth, larger pressure. Okay, so same thing here. The elastic potential energy that you have right now in this reservoir dam is actually energy in the form of pressure. So as you move from X to Y, if I call this your reference point, this point here, this is your height. This point here, this is your height. This point here, this is your height. So obviously, I would say that going here, your EPE is increasing because P increase, sorry, maybe I use a different color, it's getting a bit messy. I will say that this part here, EPE increase because H increase, P increase. Okay, I can say that the pressure here is definitely more than the pressure here. The pressure here is definitely more than the pressure here. Therefore, the EP is higher. So when you look at this statement for P and C, you're losing potential energy is actually wrong. It's actually gaining potential energy. All right. So far, so good. So answer B, answer C is wrong. Just now we're stuck at C, right? Because we see that gravitational potential energy is losing gravitational potential energy. Yes, that is correct because you're losing height, but is losing elastic potential energy correct? That is not correct because your height is increasing, or rather your depth is increasing. Your pressure is increasing because height is increasing. Therefore, your elastic potential energy is increasing. All right. So the only correct answer would thus be just D. It loses gravitational potential energy. This one is correct because height decrease. It gains elastic potential energy because your depth is increasing, your pressure is increasing, therefore EP increases. That is correct. Okay, so answer choice is D. This is the correct one. Okay, so far so good. So one thing to probably just write is that this one is A, this one is B, this one is C. Water shoots out further because it has a larger depth, larger pressure. Okay, right, so no issues here. Then I move on to the next one. Okay, then you look at question 17. A fisherman lifts a fish of mass 250 grams from rest through a vertical height of 1.8 meter. The fish gains a speed of 1.1 meter per second. What's the energy gained by the fish? They just want you to find out the energy gained by the fish. This one is a straightforward example. There are a few other types of energies here that you need to identify. Now, the fish gains a speed of 1.1 meter per second. This one you can identify as gain in KE. And then you see that the fisherman is lifting the fish through a vertical height of 1.8 meter. This one you identify as change in GP. Specifically, it's an increase because it is being lifted, so it's moving up. So your energy gain is going to be change in KE plus change in GPE, which will in turn be half mv squared minus 0 plus mg delta h. Now, where did this 0 come from? It came from here, right? Because your fish is being lifted from rest, your KE here, initial, KE initial is 0. Okay, then you reach up to a speed of 1.1 meter per second. This is your KE final. This is half mv squared. The change in KE is this KE final minus your KE initial. That's why it's half mv squared minus 0. A lot of times you will notice that the working sometimes just omit out 0. But I just write it here for you to understand why is it like that. Okay. Right, so just sum in the values and you should get the answer. Is half 0.25, change 250 grams to kg, sum in the speed, then you get the answer. Your height is 1.8. So 0.5 times 0.25 times 1.1 square plus 0.25 times 9.81 times 1.8. There is going to be 4.57 joules. So this is at 3 SF. Your MCQ questions tend to round up your answers to 2 SF. Okay, so if you want to see which is the correct answer, round it up to 2 SF. It's supposed to be 4.6. Okay, so answer is D. All right, so this one is okay. Okay, so this one is fine. Then we move on to the next one. Water from a reservoir is fed to the turbine of a hydroelectric system at a rate of 500 kg per second. The reservoir is 300 meters above the level of the turbine. The electrical output from the generator is driven by a turbine at 200 amps at a potential difference of 6,000 volts. What is the efficiency of the system? Okay, right, so if there's nothing here, let me just clear off the drawing. Okay, so what they're saying here is this. It'd be better if I just draw out for you. This is your reservoir. Okay, you have water from a reservoir that drives a turbine. Okay, and then after that, what they tell you is that the reservoir, the electrical output, turbine and generator. Okay, water from reservoir is fed to the turbine hydroelectric system at rate 500 kg per second. The reservoir is 300 meters above the level of the turbine. Electrical output from the generator is driven by turbine at 200 amps, blah, blah, blah. Okay, so this is what you can see if you try to visualize what's happening. Oh, maybe I draw it here. This is your turbine. Your reservoir is say 300 meters above your turbine connected to your generator. Okay, so when your water is flowing from here to here, you will have a loss in GPE. Okay, from here to here itself, you will have a loss of GPE. But then after that, from here, you would have electrical energy generated. Okay, in other words, when you go from here to here, how will I do this? When you go from here to here, GPE is converted to electrical. Okay, but the process is not going to be 100% efficient. Okay, because you see a question already told you what's the efficiency of the system. So what you can see here is that efficiency is energy output over energy input. Energy output is actually your electrical energy divided by your GPE. Your electrical energy, this one is going to be related to okay, you do this one here, you will get stuck because your quantities are in terms of energy. You actually would need to change this to power instead. Energy is P out over P in. Is the power of the electrical portion divided by the GPE divided by time portion. Because what you see here is this, you see, your electrical output of the generator is giving you 200 amps at 6,000 volts. The product of these two is this. You're going to get power instead. Sorry, you're going to get power instead. So you cannot use energy. All right. This one I cannot use because product of V times I is actually power. If I want to find energy, I can, but I don't have the time. You see, E power is also E divided by T. Vi equals to E divided by T. So E, sorry, E is VI T. So your main problem here is this. You don't know what is the time. So therefore, I don't use this. So I straight away use power instead. So I don't need to consider the time because I just don't know the time. Okay, that's why I don't use this one. I use this method instead. All right, in terms of power, where is energy per unit time. So this one would be VI. This one will be mg delta H divided by T. Now delta H over T, sorry, M divided by T is something that you actually have also. Let me just rewrite this properly for you. You have VI MT G delta H. Now you will see you actually have everything here already. You have V, you have I, you have G, you have H, which is 300 meter. And then the M over T is actually this one. This one is actually mass over time because you see it's kg per second. So this one is actually mass per unit time already. You actually have everything here to work with already. So you sum in everything. Sorry, let me just write it at the top. It's at the bottom of my screen, so it's a bit hard to write. So this one will just be 200. So this one will be 6,000 times 200 divided by 500 times 9.81 times 300. So it will be 6,000 times 200 divided by 500 divided by 9.81 divided by 300. You're going to get 0.815. Okay, but this is in fraction form. You want to change it to percentage form, you just multiply by 100%. So it's 81.5%. This one is times 100% to get it in percentage form. Okay, so again, this is in 3SF. You round it up to 2SF, it's going to be 82%, which is answer D. Okay, so this is the efficiency of that system. So far, so good. Okay, so this one is fine. Then we move on to one other question. Okay, now the gas in an engine does work on a piston or cross-sectional area 80 centimeters square. The pressure on the piston has a constant value of 4.6 times 10 power 5 Pascal. How much work is done by the gas on the piston when it moves through a distance of 25 centimeters? So whenever you see mention of gas, and then you see mention of pressure, constant pressure specifically, and then after that they ask you work done by the gas, automatically you should just know, you should just use this work done by gas is equals to pressure times change in volume. Pressure here is going to be 4.6 times 10 power 5. Okay, before I move to that, change in volume is actually area times distance. Okay, you already have your cross-sectional area 80 centimeters square, and you also have your distance moved. Okay, so this is your change in volume. Okay, you take your area, multiply by the distance moved. This one will be your change in volume. Okay, maybe I shouldn't draw it here. Maybe I should just draw it here. This is your area 80 centimeters square. Okay, so your distance move is this one. Area times your distance move would be your change in volume. So just sub in whatever you need to. This one will be 4.6 times 10 power 5 times area. This is where you need to be careful a bit. This is centimeter square. This is also centimeter. You need to change centimeter square to centimeter square. So let me just write it out. 80 centimeter square is the same as 80 times 10 power minus 2 meter square. So it's 80 times 10 power minus 4 meter square. Okay, so your area is actually 80 times 10 power minus 4 times 0.25. Okay, you notice that the choices of answer here, they have the same base magnitude, but the powers are different. So there's a trick here. You need to realize that you need to change the centimeter square to meter. Okay, so 4.6 times 10 power 5 times 80 times 10 power minus 4 times 0.25. You're gonna get 920 joules, which is actually 9.2 times 10 power 2 joules. Answer is A. Okay.